So today's speaker is Professor Justin Dressel. Justin did his PhD at Rochester University under the supervision of Professor Andrew Jordan. He graduated in 2013 with a thesis titled Indirect Observable Measurement, an Algebraic Approach. After his PhD, Justin held postdocs at Riken in Japan and later at the University of California in California. In 2015, he relocated to Chapman University in Orange County, where he's now associate professor. Justin's research is both impressive in its breadth and its prolificity. During his PhD, I've counted at least 11 articles being published on topics ranging from gravitational redshifts to path integral approaches in quantum mechanics. Justin is an expert on contextuality, weak values, field theories, and quantum measurements. And today, Professor Justin Dressel will tell us about his exciting work on developing new techniques for quantum error correction. So with these words, Justin, the virtual floor is yours, and please take it away.
Wonderful. Well, thank you for that very lovely introduction, and hopefully I can live up to some of that praise here. And also thank you to all the organizers for inviting me to this lovely seminar and having me give a talk. So let me pull up my slides here and hopefully. So I wanted to talk about a lot of things today, but about work that I've been doing with an experimental team at UC Berkeley led by Irfan Siddiqui. We've had a long collaboration between Chapman and Berkeley and done a large number of projects and are continuing to work in superconducting quantum computation and building quantum hardware. It's been a very productive collaboration, and I know personally, as a theorist, I really enjoy working closely with experimental teams because you tend to learn how things actually work as opposed to how you think they work. So I'll be focusing today on a topic called continuous quantum error correction. And I'm going to assume that a large fraction of the audience may or may not know much about either error correction or continuous measurements, and certainly not the joining of the two. So I'll start at the beginning, and hopefully everyone can get a little something from this talk. So this is what I had in mind here for the outline. I'll go over a bit of just basic error correction, focusing on kind of the simplest case that we are working with just bit flip error correction for 3 qubits, and go into some of the subtleties there. And then talk a little bit about superconducting quantum hardware, which is what we use to implement this idea in the Siddiqui lab with nice little superconducting devices called transmon qubits. And then I'll go over kind of the actual experiment that we did. And then if there's time and interest, I have endless extra slides of other things that we've done with these kinds of systems. So I tack them at the end just in case. Without further ado, I'll start with bit flip error correction and how this works for both 3 classical and quantum bits, just to refresh everyone's memory. So first of all, just as a side comment, if we had an idealistic Platonic world, all computations would be executed perfectly, hardware would always work, we wouldn't have any of these issues. Given an input like this function over here, I don't know if you can see my cursor or not, but given such a function, then you'd get some expected output. And these are actually taken from student work recently. And an actual problem I gave them. So here's a function, and I asked them to graph the function. It's a speed versus time, and here's an expected plot that, say, Plato himself might make of what this function looks like. But of course, in the real world, we don't have it happen quite so nicely. So this is what another student gave for the same problem. So given the input data on the left, the computational task of graphing the function, this is what the student managed to output. And they say the devil is in the details, and I think the details are devilish enough in this answer. It's enough to make a grown professor weep. So the point is that reality is not Platonic, and we should always expect errors to occur, sometimes very bad and unexpected errors. So the key question is, how do we detect those errors when they occur, and how do we correct them? So for the simple case of just classical bit flip errors, where bits are 0 and 1, there's a very simple way to do this, where we just use redundancy to kind of protect the data and allow us to fix any errors that happen in the data very easily. So for example, we take a bit 0 and we just make it a triplicate. Bit 1, we make it a triplicate. And then if any one of those bits of the 3 redundant bits flips, then we can just use majority voting to say, oh, this must have been actually a 0, and this must have been actually a 1, and then we can just fix the error. So a very simple idea, just using redundancy to fix the problem. But in a quantum computer, we have this extra freedom where now our bits can be in superpositions. And so we want to use the same kind of idea, but we also want to preserve the fact that we have superpositions. So how does this work? What we do is we encode a logical qubit, which will actually be kind of our protected data. And we do the same kind of idea of just duplicating the bit information. So instead of just a single qubit 0, meaning the logical 0, we'll have 3 qubits all in 0, meaning the logical 0, and similarly for 1. But now we have these coefficients alpha and beta in a superposition, and that's where all the quantum information is actually being stored, is in those coefficients. And what's important is that if we just look at what a bit flip does, this bit flip indicated by this X here will preserve the quantum information of a superposition encoded in this way, but because it preserves these coefficients alpha and beta. But what it does is it changes the encoding. And if I look carefully at kind of these 3 examples down here, you see that psi 1, the first bit has been flipped. And I still have something that looks very similar to psi 0 if I just relabel 1, 0, 0 meaning logical 0 and 0, 1, 1 meaning logical 1. So in some sense, what we've done is we've changed the encoding, we've changed the labeling of our basis states, but we've preserved the quantum information. And this is why we can get away with this kind of thing, is because the bit flip itself doesn't destroy the information. As long as we can keep track of kind of the label changes and then fix the labels, then we can preserve the information, which was the goal. But the trick is, how do we actually detect whether one of these bits is flipped in some majority voting kind of way without projecting the state back into an eigenstate? And the way this is typically done is you use what are called parity syndromes. Because they're value agnostic. I don't really care whether the values are 0s or 1s. All I care is whether they're the same or they're different. That's enough to do majority voting. So I pick a pair of qubits like 1 and 2 here, and I'll make a Z1, Z2 parity such that if I have even parity, if Z1, Z2 is +1, these bits are the same, and I know that there is no relative flip between the bits. Similarly, in odd parity, when Z1, Z2 is -1, the bits are different, and I know that one has flipped relative to the other. And since I have 3 bits, it's sufficient to take 2 parities, Z1, Z2, and Z2, Z3, in order to determine kind of the relative sign of all 3 bits. And we get a nice little table, which is called a syndrome on the right here. So that if I look at both of these parities, Z1, Z2, and Z2, Z3, then I can read out what all the values of those parities could be. And I get a map of what flip I would infer from those parities. So if both are even, I know all the bits are the same, and I can infer that no bit flip happened. So I get 3 idling operations. If I get a -1 and a +1, then I can infer, oh, the first bit must have flipped. So I get an XII type of operation and so forth. But in addition to kind of figuring out which bit flipped and all of that, looking at these parities has a secondary feature that's very important in quantum mechanics, which is that the act of measuring the parities just by itself is forcing these observables, Z1, Z2, and Z2, Z3, to collapse into an eigenstate of those observables. So the act of measuring these syndromes, it will project the quantum state back into parity eigenspaces. And that doesn't sound that important offhand, but what this means is that any single qubit drift errors that occur, so for example, if qubit 1 is slightly rotating a little bit away from 0 and 1, so I'm getting an analog angular drift error, the act of measuring the parity will actually force qubit 1 back into 0 and 1. And it'll either pin it into where it was and prevent it from evolving, which is known as the quantum Zeno effect. And so I get Zeno pinning of the qubits into that encoded state, or it's going to accelerate that analog drift and convert it into a full bit flip. So it'll flip 0 all the way to 1 and then pin it at 1. And so you can think of it as converting these slow analog drifts of angle into kind of big discrete jumps between these eigenstates of the parity, which happen to be the 0 and 1 encoding states as well. And this is very nice because now I've taken an analog problem, which is notoriously difficult to fix, and I've converted it into a digital problem of just classical bit flips, and I can really start reasoning about it in the same way as the classical bits. Okay, and just yes.
Interrupting you briefly, there was one question on the previous slide, Justin.
Yes.
So an anonymous attendee asks, if the parity measurements collapse the state, how come the information is not lost?
Very good question. So because I'm not collapsing to an individual state, but instead I'm collapsing to an eigenspace that has that parity, all that means is that I will get superpositions of states that have the same parity. So if I look at, say, this psi 0 state here, and just focus on the first 2 bits, notice that 0, 0 of the first 2 bits has even parity, and 1, 1 has even parity. And so if I'm measuring the parity operator, and I project onto the even parity subspace, which is what it'll push it into that subspace, then it won't affect 0, 0 or 1, 1. So it's not going to disrupt this superposition of 0, 0 and 1, 1. But if either of those qubits were starting to drift somewhere else into some other subspace, then by measuring this parity subspace, it'll put it back in this 0, 0 and 1, 1 superposition like this. So the reason this works is because what we're projecting onto isn't a one-dimensional subspace like we might be used to. It's actually a higher dimensional subspace where I can have some room to fit these superpositions into that subspace. And then what measuring the syndromes is doing is preventing me from going outside of that encoding subspace. It just projects me back into it, or projects me into a flipped version of it where I've changed the encoding like below. Does that adequately answer your question?
So I think that was a really clear answer. If it wasn't, the person can write again, but thanks.
Good. Okay, and just to highlight what I mean by this change of label, we can actually make what's called a finite state machine out of this and realize that we have 8 total bit encodings that we can make of the same superposition that don't lose any of the superposition information contained in those alpha and betas, where 0 here is this kind of I situation, or no bits initially flipped. And what happens is every time that a bit flip occurs, I'm going to go to a different encoding following one of these edges of this graph. And so I'll either stay where I am if no bit flip occurs, or I'll go to a nearby node along one of these arrows if a bit flip occurs. And you see that as I just track bit flips, I'm going to traverse this graph, this state machine. And so as long as I keep track of where I am in this diagram, I can always decode the quantum information because I can always flip the bits back to where I expect them to be, and then decode all my information. So what this means is I actually have 2 different routes to quantum error management, let's say, when I'm detecting bit flips. One is that I can track them passively. So as long as I know that a bit flip happened, I don't actually have to do anything about it. I just have to say, oh, my label needs to be updated. I'm in this different encoding 1 now, rather than encoding 0. And as long as I track every bit flip, then that's sufficient to just track everything that happened. The other way to approach it is kind of what you might normally expect, is that I'll just notice a bit flip happens and then go and actively correct it. And what I'm doing in that case is just forcing myself back to some expected fixed encoding, like this encoding 0, and saying I prefer to be there for some reason. Let's stay there. And we'll see later why that might be advantageous. All right. So if I can just track bit flips, that sounds well and good. What else can go wrong? Well, the problem with this particular code, just this 3-bit code, is that if I have more than one bit flip, then I can end up in situations that have identical syndromes, parity syndromes, but are actually very different encodings. And this means I can produce a logical error if more flips happen than I'm able to detect. And so just as an example here, I have all 8 encodings, and you can see the syndromes on the left that I'm able to see, and there are only 4 possibilities given these 2 parities. But there are 8 total encodings, and so it's a double cover. And in fact, an encoding like III, which is the base encoding, and its complementary encoding, where I flip all the bits of that encoding, have the same parities. And so I cannot distinguish those 2 encodings just by looking at these syndromes. And the same is true for all the other kind of 4 main encodings of single bit flips. If I just look at the complementary bit encoding, then I cannot tell the difference just looking at the syndromes. So if I end up in the complementary encoding accidentally, without realizing that's what happened, now I'm just going to incorrectly identify what my labels are, and I will not be able to decode the quantum information correctly. And that gives me a logical decoding error when I finally try to read something out of my state. And of course, this will happen if I have 2 bit flips, for example, for these bottom 3. If 2 bit flips happen, but I only thought that 1 happened, then I'd get a logical error because I missed 1. Or if the top one of 3 bit flips happened and I didn't notice and I thought it was just 1, then I'd end up with this top case of flipping into this logical error subspace, this complementary subspace. So that's how we get logical errors, even though we have protection from this quantum encoding. So if I go back to my graph, I can sort of split it in half and say there's a good half of all the encodings that I have access to from a single flip from where I am. And then there's a bad half where I'll get into that if 2 flips happen or more, and I didn't actually see all the flips. Put more practically, single bit flips need to be detected fast enough to avoid these complementary encodings and logical errors. I need to detect all of the bit flips, or I'm going to run into this problem. So any undetected bit flip will lose my quantum information because I've gone to a complementary encoding without realizing it, and then I won't be able to decode my state correctly. Now, if you think about this for a second, what this means is that I need to detect these syndromes as fast as possible. And so the ideal kind of Platonic way of doing things, so Plato would approve of this, is that you should just monitor the syndromes continuously. Just sit there, grab a coffee, and just watch your parity syndromes and never look away, and then you won't miss anything. And so this is an example of what that might look like. But in the real world, of course, you can't just look at something instantaneously. Every time you try to make a determination of something like a syndrome, it'll have a characteristic time scale to it. And so what we're really saying is that there's some observation time scale of these syndromes, and the flips that occur much slower than this time scale can be detected such that they're all individual flips, and then I can track them. And then in addition to that, if I'm mistaken looking at the syndrome for some reason, which happens, that mistake will actually be fixed over time as well. And this is an actual simulation example here of a Bayesian filter reading some monitoring of some syndromes and tracking as you go through a bunch of bit flips that happen randomly. And so what you see is this, the dashed line is the actual state of when the flip happened and what the actual encoding is. And the yellow line is what we think happened based on what we observe using this kind of optimum Bayesian estimation. And there's a little bit of a time lag, which is hard to see, of when a flip happens on the black dashed line. The yellow line's a little bit lagged. And that lag is that characteristic time scale of seeing that this syndrome has actually changed. And what we're seeing here is that it basically tracks these flips very well. And occasionally the filter might make a mistake. Our Bayesian estimate might make a mistake. And that's what happened in this middle here with this red arrow pointing to it, is that our filter thought that a flip happened, but then on monitoring the syndrome further, it realized, wait a minute, no, that syndrome isn't consistent with that. And so it goes back and says, nope, a flip actually didn't happen. I was mistaken. And so it auto corrects itself without having to do anything if I just keep watching it long enough. And there are several cases here where I get such mistakes that get later corrected. So this is great. If we can achieve this, then Plato approves. He says, this is ideally good. Well done. We should always do it this way. But of course, it's not always this way. And here's a bad tracking example. Same time scales, same characteristic time scale. So I didn't change anything here, but just another random sample. And in this random sample, there happened to be two bit flips that happened in very short succession of each other, such that the second flip happened right in that window where there's this characteristic time scale, and my filter for being able to detect bit flips failed to see the second flip. And so even though my state flipped twice, my filter only registered a single flip, and now my encoding that I think it is ends up complementary to the actual encoding, which is exactly the case of a logical error. Then if I keep going from that kind of very early mistake, you see that my state remains complementary the entire time, and it never recovers from this one error earlier on. Even though there are kind of filter errors that happen again, and those filter errors are corrected, they're corrected back to the wrong encoding. So once I'm in this complementary subspace of logical errors, I can't get out of it so easily, and I've lost my information. So these double bit flips in short succession are really kind of the dangerous thing for this kind of code.
I have another question for you, Justin.
Yes.
Well, actually, it's three questions now. Okay, so let's see. So the first question was, if you just track the errors and don't immediately correct for them, if you have entangled systems where errors can happen, doesn't this become an intractable problem?
If you have entangled systems, I mean, not necessarily, because if we go back to here, what we're dealing with are superpositions here. And so I'm just taking a logical zero of a particular encoding, and I'm just duplicating that logical zero. So all the entanglement in, say, a quantum information sense, I'm going to have multiple logical bits all entangled together, but each of those logical bits is going to be sort of protected in, say, triplicate or more in this way. And so as long as I keep track of the logic or the encoding of each logical bit, then I should be able to extract the full entangled state as well, just by tracking each of the bits all the way through. And if you look carefully, all I'm doing is changing labels of what zeros and ones mean. And that means I can always go back and to this particular physical qubit, I can flip it back to zero because I know that that bit's flipped. I can always flip it back. And so I can reset all of the encodings back to my 000 encoding before I do any important operations on my state, for example. Or I can modify the operations that I'm performing so that they use the correct encoding, correct logical encoding mapping to the physical qubits. So it's not necessarily a problem with entangled states. There are other problems when I'm implementing big entangled states, but the encoding isn't one of them.
Okay, thanks. So the second question is, could you clarify why the changes of the filter are discrete? Wouldn't Bayesian filter tell us about probability distributions over 3-bit encodings? Or is this a maximum likelihood method?
Good. Yeah, so the full Bayesian filter, you're correct, is keeping track of the full probabilities. And so what we're doing here, but saying that I believe it's this encoding, is we take the maximum probability encoding as the best guess for what encoding it is. And so in that case, yes, there's continuous information being tracked behind the scenes, but when the filter tells me this is what I believe the encoding to be, all it can do is pick the encoding that has the highest probability. So it's max likelihood in that sense.
Okay. And then the final question is, could you give an example of what the thing that the filter measures is? So like, what is the signal behind the yellow line?
Yes, and in fact, I'll get there a bit later, so I'll delay answering that question in full to show you on a later slide. But at this stage, you can think of this as any observation strategy. It doesn't have to be continuous, doesn't have to be discrete, just anything that has a time scale of me looking at my syndrome, I'm going to have behavior of this sort. So it actually is kind of agnostic as to how I'm implementing this yellow line, depending on how I'm looking at my syndromes. But no matter how I look at my syndromes, there's going to be a characteristic timescale such that this behavior still happens. So if I have a double bit flip within that characteristic timescale, however it's implemented, there's going to be a problem.
Okay, and then there's been a final, I think there have been 2 more questions now. Maybe I do one of them and then we move on for a bit and then I come back, because otherwise maybe we get stuck here.
So I trust your judgment.
Yeah, I think I'll do one more question and then we'll keep the others to a bit later. So does dynamically updating the logical circuit rather than trying to immediately correct the errors reduce dead time during which you are vulnerable to 2 error flips in succession?
This is a very good question. So this is kind of looking ahead to implementation differences between these kind of abstract strategies. And you're right that if I make an attempt to correct something, then I have to do something to my circuit to implement that correction, which does take some time. And there is an extra time window there where I might be doing something and maybe not be able to observe it, depending, again, how I'm doing my observation strategy. So there are cases where it would be advantageous to not do the correction immediately because of that dead time where other errors can occur. But there are other cases where that just isn't a consideration. So a lot depends on the actual details of how you're doing the observation. That's a very good question.
And a good answer. Thanks, Justin.
That actually leads me very nicely into the next slide, so that works well. So in traditional error correction, quantum error correction, we usually think in terms of circuits and gates that are discrete in nature. And the way you do such parity measurements, so you're measuring these syndromes of parity, is that you use ancillary qubits. And this is a circuit here that does that. And so I have my 3 data qubits kind of at the top. And then I add 2 more ancillary qubits, which will be my parity measurement qubits. And say qubit 4 is going to be my Z1, Z2 measurement qubit, and qubit 5 is Z3, Z4. And if you look at how it's implemented, what I do is I take a C0 gate. So I do a controlled flip of bit 4 if bit 1 is 1, followed by a controlled flip of bit 4 if bit 2 is 1. And that succession of controlled knots is going to implement a parity encoding onto qubit 4. So then if I just measure qubit 4, if it gives me a 1 or a -1, that'll tell me what the parities were of 1 and 2. They're either both the same or they're both different. And then similarly, qubit 5 is just a sequence of C0 gates on qubits 2 and 3 in order to implement I guess that shouldn't be Z3, Z4. That should be Z2, Z3. I apologize for that. The second parity measurement. But what this means then is in order to actually observe the parity, I have to initialize my ancillary qubits to some known state. I have to implement 2 successive C0 gates per qubit. And then I have to read out my qubits, which takes some time to do the readout of that syndrome measurement. And then after that, I can await some arbitrary dead time, and then I can reset my syndromes, often with a heralding measurement. And sometimes I can reuse my syndrome measurement, add a little unitary gate here instead of a heralding measurement, and reset it that way. But if too much time has passed, I may want to remeasure it and then reset it. So there's all this stuff that happens in between, and the cycle time of this whole circuit is this big delta T that you see at the top. So that would be the characteristic time scale I'm talking about for this discrete version of error correction. It's that during this big delta T, that's when I kind of read out what the parity is, and I can't learn the parity again until at least one big delta T has passed. And so I sort of get a discrete sequence of parity results separated by big delta T. So inside that window of delta T, that's when errors can happen, like a bit flip or 2-bit flips or 3 or so forth. And so I want this big delta T to be as short as possible so that I don't get multiple bit flips happening inside that window. Now, just to put some numbers here, some example times from a superconducting implementation is that each C0 gate here would take on the order of 100 nanoseconds, sometimes a little longer, depending how people are doing it. And these times are getting better all the time, but this is kind of a realistic window of times. The measurement of a single qubit also isn't for free, and depending on the system, that can actually take quite a long time, sometimes up to 3 microseconds. But if you get very fast measurement, you can get it down to around 100 nanosecond scale, which means that your cycle time, which is 2 C0s minimum, plus at least 1 measurement, if not 2, is going to be somewhere between 300 nanoseconds and over 6 microseconds. And in the world of superconducting qubits, this can actually be fairly long. It's a lot of time for errors to happen. You remember, I need a maximum of 1 flip per cycle time in order to track it reliably. But also, I've had to add stuff to the circuit in order to implement this. I've had to add 2 qubits, and these ancillary qubits themselves can have bit flip errors and other things happen. And if that happens, that can not only disrupt what my syndromes look like and give me wrong syndrome results, because of these C0s, I can actually have an error on an ancilla qubit kind of back propagate and screw up my data as well. And this is all part of the whole concept of fault tolerance, is preventing those kind of errors from happening as well. But because I introduced extra stuff, now I have extra errors to worry about. So you can think of this as the implementation has a natural overhead to it. There are extra resources I need in order to actually implement this, which include these 2 qubits, all the gate couplings I need to get them to talk to the data qubits. I need all this readout. I need the controls for the ancillas, et cetera, et cetera. So it doesn't come for free. There's a substantial overhead cost to being able to do this.
So I'm just going to push in a quick question on a related topic here. How important for equivalence of the passive and active corrections is the fact that the errors correspond to unitary transformations of the qubits?
As opposed to some decoherence, for example. It actually, it's a subtle question. So if it's a unitary error, then what I was saying about converting analog to digital errors is very true. If it's a decoherence type error, like environmental T1, which I'll talk about later. Then it's a little bit different because it's incoherent. And then there may be a difference between passive and active if I don't start with a coherent error. And I'll show you an example later on of where that difference actually shows up.
Okay, great. Thank you.
Okay, so what we're thinking about here is an alternative way of doing this syndrome monitoring, and that's to not do ancilla qubits at all. Don't think in the circuit model. Instead, just directly look at the parities of the qubits. If there's a way to directly do that, then I don't have to have all this extra machinery of the circuit formalism here. Instead, I'm kind of limited by the hardware itself of being able to do this parity measurement. It turns out that we can do this, at least in the bit flip case, fairly neatly. And the idea here is that we'd couple some device to two qubits, like qubits 1 and 2, and this device will be a resonator, it turns out. And then we can get some signal out of that device, which turns into some time-dependent, continuous, noisy-looking signal. And I'll do the same thing for the other parity. So I end up with two time-dependent signals now, both of which are very noisy. And then the circuit cycle time is going to be kind of it'll be the noise filtering time scale. So these are very noisy signals. I can't tell anything from them instantaneously. But if I average them for a while, then it'll average away that noise and I'll be able to see the mean signal. So there's a characteristic time scale to average away the noise, and that characteristic time scale, which we call the measurement time, will replace this circuit cycle time as the characteristic time scale for seeing the parity. So just abstractly, we can say, well, what would this look like? Well, the cycle time becomes the measurement time, and then that's just the readout time scale we had before. So somewhere between 100 nanoseconds and say 3 microseconds. We don't have any other gates in between. We don't have reset times. There's no other dead time in that cycle. So we're just worried about this measurement time. That's just a conceptual simplification that's satisfying. And as far as just overhead hardware, we need to have these devices to measure the parity. So these are just two resonators and the machinery to couple to those resonators, for example, but I don't have all the ancillas and other things. So I replace my hardware overhead with different overhead, which might be simpler depending. But there's always the caveat that doing measurements can also disrupt the system if you're not very careful about how you tune the measurements. And that can be easier said than done in practice. So Plato likes this idea, says this is great, let's do that. Why didn't we do that to begin with? But then the realistic question is, can we actually do it? So I'll dive into part 2 here to say, how do we actually do this? And give you a brief overview of the type of hardware that we're using in case you're unfamiliar with it. But I'll try not to dwell on it too long. And what we're using are superconducting circuits, because if you cool aluminum, it turns out, near absolute zero, it becomes superconducting. It loses its resistance, which means it loses this dissipative feature that is usually in wiring. And that allows it to preserve quantum coherence. So we cool things down near absolute zero in a dilution refrigerator and just make circuits out of aluminum wires, and they're all superconducting circuits. Now, what's nice is that you get the usual circuit elements in such a system. You get the capacitors, you get the inductors, you don't have the resistors by design, but what you do get is an extra circuit element that only appears in the superconducting regime called a Josephson junction. And all this is a tunnel barrier, an insulating tunnel barrier between two superconducting wires. And in practice, it's an aluminum wire, and then I allow its surface to oxidize a little bit, so I get an insulating aluminum oxide layer, and then I deposit another aluminum wire on the top. So very simple to fabricate, very robust to fabricate. And this little tunnel junction then behaves like an inductor that's nonlinear. It depends on the amount of current flowing through the inductor. And so I get a nonlinear inductor element in addition to the linear inductance and the linear capacitance. And I can make very interesting circuits out of that. So a transmon, which is the most successful superconducting qubit so far, though many more designs are being explored right now, is one of the simplest possible circuits that you can make in such a system. And it's literally just a Josephson junction shunted by a large capacitor. So you can think of this as a nonlinear LC oscillator. And the large capacitor serves to screen off excess charge noise in the nearby environment. And so it protects all of what's going on in that tunnel junction. And it turns out it makes this transmon very robust to have high coherence times and all that. Now, if you write down the Lagrangian for a nonlinear oscillator like this, then you discover that it's the same thing as a pendulum, just the identical potential energy to a pendulum. And then if you quantize it, you essentially get a quantum pendulum. So you can think of this transmon as a quantum pendulum. If you draw its potential energy curve, you get something like what's shown here. It's actually a cosine potential. But if I focus on one of the wells of the cosine, then what you get when you quantize it are discretized energy levels in that cosine well. And those become non-evenly spaced due to the nonlinearity of the cosine. This is an anharmonic perturbation away from a harmonic oscillator, which would just be a parabola. And then that allows us to address just the bottom two levels because they'll have a unique energy spacing, and every other pair of levels in this anharmonic oscillator has a different energy spacing. And so I can just address that single gap between the 0 and 1 energetic states and call that my qubit and sort of ignore all the higher energy levels. So that's what we mean by a qubit as a transmon, is it's the lowest two energy levels in a quantum pendulum made out of superconducting wires. Now, this means that these act like artificial atoms, since it's like the bottom two levels of some artificial atomic potential energy well, but I get stronger couplings than I would normally see in atomic physics, for example. And so there's lots of fun things you can do with these circuits. And just to give you some ideas of numbers, the frequencies, so h bar omega q would be the energy gap between 0 and 1 here. That frequency omega q is on the order of 4 to 7 gigahertz typically. And the energy next highest pair of levels between 1 and 2 is smaller by some small amount, which we usually call the anharmonic correction or the anharmonicity. And that small little correction from the harmonic equidistant level spacing is on the order of 100 megahertz, just to give you an idea. Okay, so given that, we build up whole chips of these things. So this picture here is of an actual 8 transmon chip at UC Berkeley. And then we also build quantum limited amplifiers in order to amplify signals coming out of it, which I won't get into too much here. But just to focus in on a little bit of what these components are on such a chip, in sort of purple in the middle here is our qubit, which is our transmon. That's just our capacitive pads with that little Josephson junction connecting those two pads. And then I have some useful hardware attached to that qubit. There's a blue control wire on the left, and that's what I attach to a microwave signal generator in order to enact unitary rotations of my qubit subspace by tuning the energy of my incoming microwave field to be resonant with that energy gap of just those two levels. There's also this red readout resonator attached to the qubit, and that's what I use to read out the qubit state. It's dispersively coupled to the qubit, so it shifts its resonant frequency depending on what the qubit state is. And then I pump via this green kind of readout bus, the readout resonator at its resonance point, and then learn what the frequency difference is by reading a time continuous noisy signal of that microwave field. And that allows me to infer what the qubit state is. And then I do this a bunch on the same chip. So the actual circuit looks something like the following when I'm doing such a readout. So this red circuit in the middle here is that readout resonator, just as an LC oscillator. That's coupled to this transmission line bus in green on the right. And what you see is that that bus is pumped by some signal generator. It's reflected off this readout resonator. The reflected signal is amplified in either phase sensitive or phase preserving way, and then it's mixed with the reference local oscillator and then split into either a homodyne or a heterodyne readout signal. Homodyne would give me a single signal that's focused on one particular axis of information, and heterodyne would give me two signals which are orthogonal to each other, and I can use both of them to access the entire resonator information. And we've used both methods. So just to throw some math up here for those who are interested to see what this all looks like, starting on the right here, the qubit, which is given by these sigma z Pauli type operators, typically is dispersively coupled to the readout resonator, which is described by these lowering operators A, that it'll have some dispersive shift chi, which is the amount that the resonance frequency of the resonator shifts up or down depending on the qubit state. And you get a Hamiltonian form of roughly this diagonal coupling on the right. The readout resonator itself is, of course, diagonal in A dagger A. The readout resonators are detuned from the qubit by about 1 gigahertz typically, but are still in the like 5 to 7 gigahertz range typically. And they have some amplitude decay rate cap/2 leaking into this, traveling green readout line. On the left, we have our control line, which is driving the qubit with effectively a sigma x via capacitive coupling at resonance. And then we can do Rabi type controls with the sigma x and then use phase offsets of its natural rotation around z in order to access the entire qubit state space with just a single control like this. So I know that's too fast to get too much out of, but hopefully it gives you an idea of what these systems are and how they work. But more relevant to our task is that given such a setup, then the way this measurement works is that I'm getting a very noisy signal out that's either heterodyne or homodyne. For our case, we can think of it as homodyne, just some very single, very noisy signal. And given this time-dependent signal, which looks something like this graph here, it's just featureless white noise is what it looks like, we have to filter that in some way. And our task with measurement is either one, which is what we typically have been doing recently, is to learn what the qubit state is doing from such a noisy signal. And this is called quantum filtering or learning the quantum state trajectory from such a readout. Or two, we can learn what the mean observable as evolution is from such a noisy signal. Now, the measurement rate, gamma, is set by the strength of the readout drive, and this is going to be related to the time scale of how long I have to integrate in order to get unit signal to noise ratio. And so this gamma will be related to our cycle time in our continuous setup.
There's one question here, Justin. I anticipate that you might be just about to answer it, but on the slide we've just seen, someone asked, how should I think about the y-axis of this data in terms of what happens to the qubit?
Yeah, that's a tricky question. It depends what I'm measuring, of course. But this y-axis is a voltage, which is in arbitrary units to start with. I have to rescale it and shift the voltage to get it to be calibrated to anything particular about the qubit. But typically, I'm measuring something like the z observable, which has two eigenvalues, 1 and -1. So if I scale and shift this voltage just right, I can set it up so that the average voltage will be at, say, +1 when I average away the noise, or the average voltage will be at -1 when I average away the noise, depending on what the value of z is. So if I have a fixed value of z and I read it out for long enough that I can average away that noise, then I'll see the mean of the signal will tell me directly what the eigenvalue is of z and give me information of that. But it depends upon me actually calibrating the signal carefully for that to be true.
Okay, and we just had another question in the chat. So could you comment on the fluctuations of the measured current? So although they're small, they're not exactly vanishing. And will they not accumulate over the running time of the experiment? So
yeah, so the structure of the noise here is it's very close to white noise, which means that I'm going to have a zero mean kind of white noise looking portion to the signal, and then the mean itself that white noise is around. Now, what the oscilloscope and whatnot actually records, which is a subtle point, is that any oscilloscope has natural bandwidth to it. And what that means is it's averaging over very tiny time bins, delta t. And so, for example, if it has a gigahertz bandwidth, you'd expect effective delta t's of like a nanosecond. So each of these points that you see here on this plot is actually kind of a time bin average of a nanosecond as a discrete sequence. So it's not truly continuous as a function here. It's actually small little averages. But I can think of each of these bins, delta t, then as sampling from a Gaussian distribution centered at whatever the mean is with a variance set by this averaging window, delta t. There's going to be some characteristic time scale, say tau, divided by delta t, and that'll be the variance of the signal of a single one of those bins of length delta t. And so we have a very detailed knowledge of how the statistics of this works, and that's actually why we can get away with integrating away the signal for a while, which just increases the signal to noise by averaging away the zero mean noise part. And as long as my mean doesn't change during that averaging window, then I get better and better information about that mean as I average.
okay, thank you.
Yeah, these are good questions, and it's subtle, and I know I'm going through it quickly here. But maybe this will help. So there are two regimes, sort of two extreme regimes of such a readout device. So there are a bunch of parameters, which I list up above, and for time I won't go through all of them in detail. But the point is I can tune like the drive strength of the measurement drive, for example, to go between these two extremes. And so if I start on the bottom here, this is what's called a weak measurement regime. And what this means is that my means, so if I imagine my z having plus and minus one eigenvalues with a whole lot of noise around it, these Gaussian curves you see here are the probability distributions of that noise around each mean that it could be. And so I'm going to get an overlap of two Gaussian curves. And if I'm in this weak measurement regime, these Gaussians are quite broad, which means that I have very noisy data. The noise fluctuates over a much wider window than the separation between my eigenvalues. And then I'm going to get a signal, sort of like the middle bottom plot here, where I just can't really tell which eigenvalue things are, even after averaging a bit, because the noise is just too large. In that kind of situation, you get what's called diffusive quantum evolution, and you get diffusive quantum trajectory evolution, which is very interesting, but that's maybe not so useful for this particular use case. So instead, what we do is we turn up the power of the measurement drive, which then just shortens the time scale that I have to average in order to remove the noise. So what that means is for the same length of time bin delta t, I'm going to get histograms of noise around the means that are much narrower like this. And when they're narrow like this, there is some overlap still, but it's much smaller. And that means I'll be able to see two distinct peaks, two distinct means show up right around the eigenvalues of what I'm observing. And instead of seeing diffusive evolution that sort of goes all over the place, what I'm going to see are fairly well-defined jumps between these two means. And the reason for that is because this is in a faster projective type regime, it's actually projecting the quantum state onto these eigenvalues, eigenstates. And in order to get away from one of the eigenstates, it actually has to get measured all the way onto the other one. And so it gets projected onto the opposite eigenstate. And so I get jumps between the eigenstates on about the time scale of this measurement collapse rate. So you can actually estimate what this this collapse time tau has to be just from looking at these jump diagrams. And so we have two ways of filtering. One is to get the full quantum state out, which would be these right plots, and that would be getting the quantum trajectory itself. But for what we're doing, it's actually sufficient to do these middle plots and just look at the trajectory of the syndrome itself just by filtering away the noise. And for such a Gaussian white noise type process, a simple exponential filter, moving window exponential filter, is adequate for doing this, as long as we're in this kind of top projective regime. And just to give you an idea what this looks like in more detail, on the left, here's this weak syndrome tracking where you see we don't really track what's going on very well just by averaging the noise. But as long as we have a strong enough measurement, then when we average the noise, which is what this orange window is, it's just an exponential filter of the raw readout noise, properly normalized. And we compare it to the actual state evolution as it's jumping back and forth between these eigenvalues. You see that it matches actually quite well up to a very small delay, which is again on the order of this measurement time. So that's where we want to be if we want to continuously measure a syndrome. Okay, I know I have like 5 minutes left, so make sure we get to the meat and potatoes here. So that's kind of the highlight of what the hardware is, how we expect to implement it. So let's see what happens when we actually do implement it. And this is out of a paper that came out fairly recently in Nature Communications here. But the Berkeley team spent quite a bit of time optimizing this chip to get all of the fabrication design parameters carefully executed well. Turned out that was quite a bit harder than it seems like it should be. But this is a 3-qubit chip. There's the 3 qubits in the middle here. Each of them is connected by a readout resonator, either this blue or red resonator, such that each resonator touches 2 qubits. And those will be the parity readouts of each of these pairs of qubits. Each qubit also has a dedicated control line coming in from the outside, where I can manipulate the state of each qubit independently. And each of these readout resonators is connected to just a separate readout bus, if you like, so that I can pump them independently. I have a readout generator on the bottom here sending out 2 separate signals, one that pumps readout 0, the other pumps readout 1. And then I get 2 separate noisy time-dependent voltages, just like you saw earlier. Those get fed to an FPGA. And the FPGA implements the moving window exponential filter, as well as rescaling anything and shifting it as it needs. And then it monitors these 2 parity signals, and then it will enact active controls to these qubits as warranted from some internal algorithm. So fairly simple setup, just as a proof of principle to see, does this actually work? And we can optionally either passively track or actively correct with this FPGA, which is important. And you can say, well, how do these resonators measure the parities? And that's a little bit tricky, but very quickly, what happens is that we arrange the dispersive shifts, these chi, to shift the resonator frequency up or down by the same amount, so that the odd parities get shifted one way by one dispersive coupling and get shifted the other way by the other dispersive coupling and end up back at the center. So that if all my dispersive couplings match up identically, then my odd subspace actually doesn't have any dispersive shift in the resonator, but the even subspace ends up getting shifted twice, either one direction or twice in the opposite direction. And as long as my dispersive shifts chi are larger than the line widths of my readout resonators, then these double shifts will place it fairly well outside of the resonance zone. And that means if I pump my resonator right on the symmetry point, this dashed line, the frequency there, then I'm going to populate my resonator to a steady state if it's in the odd subspace. But if it's an even subspace, I'm off resonance. And so that means that my microwave field in my resonator will remain largely in the vacuum state. And so I'll end up with one of two states of the resonator, which have degeneracy of what qubit puts it in that resonator state. And that's the key to having a parity measurement, because I want this kind of degeneracy. So I either have a well-populated resonator, like here in green, which is the odd subspace, or I'll have something near the vacuum, like this purple, which will be the even subspace, except you'll notice that it's not perfectly in vacuum because there is still a little bit of overlap on each of these two sides. And so I'm going to end up with a little bit worse behavior in this even subspace than in the odd subspace. Okay, so with all that hardware, then we can flip on our FPGA, flip on our filtering, flip on our correction, and see what happens. And so this plot on the right, let's start here, is actual voltage scaled so that the eigenvalues of parity are at plus and minus 1. I have two signals here, one for Z1, Z2 parity, the other for Z2, Z3 parity. And if I do nothing to the system, you see that they both hover around a particular eigenvalue, just showing that no flip happens. Now at this 10 microsecond mark, I can induce a bit flip just by literally flipping one of my bits with its control to see what happens. And the filter will register, yes, a bit flip happened on some time scale, which is related to that measurement time. Once it passes some threshold so that I'm certain, yes, a flip happened according to that readout, then I can apply a correction pulse and flip it back. And then you see the blue curve is walking back to where it started to show that not only did it detect the flip happened, it detected the correction happened as well. So that's great. It seems to work exactly as predicted. This plot on the left is then showing a handful of such trajectories of these parities as just a 2D plot. So rather than having two signals, we can just parametrically follow a curve here in this 2D plot. And so if no error is happening, we'll hover around this upper right quadrant here. But if we get a bit flip, then you'll see that the signal will start wandering into a different region. And we can just demarcate these regions as where we know one bit flip has occurred, or we're in some complementary subspace. And so if we wander into a region past some threshold, which are these dashed lines, then we can apply a bit flip, which is this pi symbol here for a pi pulse, flip it back, and then watch it wander back over to indicate that there's no more error. And this works great. We do this for a large ensemble just to see kind of typical traces that we see. This is an ensemble where I induce a flip at this time here of qubit 0 just to see what will happen. And now I can compare kind of two different ways of doing correction. Red is passive, so I just watch the flip happen and don't do anything about it. And notice that in these red curves at the bottom, it just tracks I'm in that syndrome. So I know that flip happened. As long as I'm paying attention, then I can know what encoding I'm in. And also notice that these orange horizontal lines I put here, that's my characteristic measurement time for filtering the noise. And you see that this transition of the filter certainty is happening on a few of these tau timescales, exactly as you'd expect. And the blue is the active correction method, where I see that a flip's happening, then I actively flip it back, and then I watch the blue curve go back to where it started. And again, you see that with an active correction, it takes me about 3 tau or so to detect that a flip happened, implement the bit flip back, and then see that my filter is restored back to its original state. Now, this is what is related to an earlier question. What happens with incoherent processes? Like T1 is the most infamous one, which is related to energy relaxation caused by environmental noise, coupling to some environmental degrees of freedom, where a qubit just relaxes to its ground state suddenly. And on average, this is described by decoherence rate T, or decoherence timescale T1. So the longer this timescale T1, kind of the better protected your qubits are from your environment. Shorter T1 is, then the more rapidly the environment's just absorbing all your qubit energy, which is what you don't want. Now, what's interesting is that we applied this. We can say that for a single qubit, its natural T1 timescale is this green dashed line here, which is about 20 microseconds. And if we just turn on our system, then because we have kind of this triplicate of qubits representing a single logical qubit, then when I look at the logical T1 passively, it actually does worse than the single qubit. So this is an overhead effect of just the redundant encoding. I'm also multiplying these natural environmental errors, which makes it look worse before it gets better. But then this is where the active feedback starts helping us by actively correcting bit flips when I see them, rather than just tracking bit flips. Then I can actually fix this T1 and do better than the single qubit performance. So this orange curve is when I turn on active correction with this bit flip code, and you see it actually does considerably better than the bare T1 timescale of just a single qubit. So I'm actually getting a massive improvement here. Well, maybe not massive, but a substantial improvement just from turning on error correction. So it does help against incoherent errors, provided that we do active correction. So there is a benefit here to the active method. I know I'm over time, so I'll quickly just mention that total measurement timescale is actually made out of not only the measurement filtering, but then there's signal delays, there's delay of enacting the FPGA signal, et cetera, and that all goes into this tau. And when we do some tests where we do 2 consecutive flips delayed by some fixed amount, then this blue curve here is basically the probability of what we want. The orange curve is the probability of what we don't want. As long as the time between flips is longer than this measurement time, then we do pretty well. As soon as the flip distance between flips starts becoming less than our measurement time, then we start getting these logical errors of things we don't want. And we can try many different permutations of pairs of logical errors, and we see this behavior is pretty consistent. That timescale, the measurement timescale, is fairly robust, exactly as we expected it to be. And it's nice to see that works. And I'll skip over this for now and go to conclusions so I don't wear out my welcome here. But the net point is that we can do direct parity measurements, at least for this 3-qubit bit flip code, and it works pretty well. And this method is potential for reducing hardware overhead and cycle time overhead and all these things. But we'll caution at the end here that this is a proof of principle of only bit flip correction. In order to do true quantum error correction, we also need to protect against phase errors, which are completely outside the scope of this code. So that's ongoing work to figure out how to get both implemented in such a direct fashion. But at least proof of principle for the bit flip code seems to be working well. So thank you for listening.
Thanks so much, Justin, for this great talk. I held off a few questions so that we'd give you some kind of breathing space to actually finish off the talk. But I'll go back to these questions if you have time to stay with us for a bit longer.
I have time. I'm just sensitive that other people may not have time. So, but I'm happy to answer questions.
Yeah. Okay. So I think the first question was from quite a few slides back, where you had the 2 narrow Gaussians and the 2 broad Gaussians. And the question was, why are you sampling at different time scales?
Sampling at different time scales.
I think the axis on the narrow peaked one goes to 20 microseconds and then to 2 microseconds on the broad peaked.
Oh, you mean here?
Yeah.
Yeah, so this is related to the fact that I need longer averaging times for these wide Gaussians in order to get down to something that looks clean in this middle plot. So if I didn't do long averaging, then the middle plot would just look more like that and be way off the scale. So notice that here the numbers are like minus 30 and 30, as opposed to the eigenvalues being plus and minus 1. So what this middle plot's actually showing you is an exponential filter after a long averaging window to get the noise down to some mean that actually is some reasonable fluctuation. And it shows that even after such a long average, it doesn't really track those eigenvalues very well. It's much more diffusive. So the reason, that's part of the reason for the difference. The other reason for the difference is that on the top plot, which actually has much longer time scale, I'm getting pinned to these eigenstates for a long time. And so if I had a really short plot, then it would look very uninteresting. It would just be kind of flat. So instead, what I'm looking at is a very, very long time. So you can actually see a couple jumps that happen between these eigenstates, as opposed to just looking at a flat line. So I think that's the other reason, that they're just different end times on these plots.
Okay, great. So next question, can you comment on the effect of changing the measurement rate, weak versus projective, on the effectiveness of the continuous measurement as an attractive force keeping the state in code space, as opposed to the effectiveness of detection errors to correct them?
Yes. So you can actually see that on the plots on the right here of the actual state. This is for a single qubit Z operator, but it's basically the same behavior. So that when I'm in a stronger projective measurement, I'm actually getting pinned to the eigenstates. You see on the right, this black line, which is the Z coordinate of my qubit, is getting pinned to either -1 or 1. And if it tries to deviate away from it, like you see these little bumps, then it immediately gets pushed back. That's the quantum Zeno effect of it getting pinned to one eigenstate. And the stronger my measurement is, the faster this measurement rate, then the stronger this pinning, this quantum Zeno effect is. And that's exactly the same effect in the parity case that's pinning us to our code space. So we want kind of the fastest measurement we can in order to have the largest amount of protection in this sense. If we weaken our measurement, like in the bottom plot, then we're allowing this diffusive behavior of the state, which doesn't particularly have to remain pinned to those code space eigenspaces at all.
Right, that makes sense. And then we had on a couple of slides forward, where you have these 2D voltage plots where we're moving around. I think this is what the question refers to. Why does the demarcation have zones between the flipped regions? So I guess why is there some space in between?
Very good. The reason for this is much like the earlier plots I had when there was a question about the yellow line of whether this was a maximum likelihood estimation or something of that sort. The point is that I have these signals of these parities, and they don't tell me exactly what's going on. They give me noisy information about it. And so I have to make a decision at some point. Do I have enough information that I'm certain a flip happened? Because it might just be statistical fluctuation that it wandered up for a little bit and wandered back down. And you can see that, say, in this plot on the right, this blue curve sort of wanders up around, say, 8 microseconds, but then wanders back down just from statistical fluctuations. And so if I set my certainty too sensitively, in some sense, then I'm going to erroneously think a flip happens just due to noise fluctuations. So what I want to do is put my decision thresholds far enough away that they're very unlikely to cross that threshold unless a flip happened. But I don't want to put them too far away, because then that's just increasing the amount of time required in order to register a flip, which invites more flips to happen sooner. So there's kind of an optimization you have to do of where's the best place to put this threshold. So on the plot on the left, these reddish brown dashed lines are the thresholds in this 2D plot for when I decide an error happens. If my curve passes those dashed lines, I say, aha, I'm certain enough that a flip happened, so I'm going to operate as if a flip happened. If it didn't, then I'm going to learn otherwise by continuing to watch the signal, basically. Now the plot on the right, there's two dashed green lines. The reason for that is that when I go from, say, the -1 state to the +1, when I cross the top of these green lines, that's my decision threshold for flipping that direction. But then when I go back down, I don't want to immediately flip at that same line. I want to have kind of a symmetric distance away from where I think it is. And so I actually need two thresholds, one from a flip one direction and the other for the flip the other direction. So they're conditional on the state that I think it actually is.
Okay. Maybe last two questions then. So the first one is, it is often said that the continuous error correction is an open problem. Is it because of experimental difficulties, which were very nicely explained in this talk, or intrinsic imperfections? For example, continuous syndrome measurements have fluctuations, or some missing theoretical result?
So I can interpret this question in a couple ways because people mean different things when they say continuous error correction. So here what I'm talking about is continuously monitoring the syndromes, and then I can have actually discrete correction pulses. So I flip the qubit discretely when I think it's wrong. That's actually different from continuously correcting the qubits, which is another thing I could do by feeding back the continuous signal and then having a continuous drive on my qubits that depends on that feedback signal. That's another version of continuous error correction, which has been studied at length, I think, theoretically. I think the conclusion of the continuous error correction, where I always have a correction happening that's dependent on my readout, is that it's always kind of worse. It doesn't really do all that well, because especially once I get the feedback delays in the problem, that delay is enough to really kill the fidelity of such a protocol. But in this case, if I just continuously monitor the syndromes and then apply discrete correction pulses periodically as needed, that seems to work pretty well. And I think that's been less explored, others in our group, until recently. And as you see here for the bit flips, it actually does work very well. The missing part experimentally is really getting the phase protection in this continuous way. That turns out to be quite challenging, just to find an experimental implementation that does that well. And then being able to do both the bit and the phase and in suitably enlarged encoding to get full quantum error correction is still an open problem. So this is a stepping stone proof of principle of part of the problem that needs to be solved, but it's not complete yet.
Okay, and then final question. So you've talked about parity ZZ measurements here. Do you anticipate that your setup will work to do an XX continuous measurement in a similar way?
Yeah, and this is the same question as the phase protection, essentially, because if I pin Z to be bit flip as a meaning, then X is going to have essentially the meaning of a phase flip. And so if I can do an XX measurement, that would be a phase parity measurement as opposed to a bit parity measurement. And it's exactly that XX phase parity measurement that's not trivial to do. I know how to do it using dynamical, like paired rotations of qubits, but it's particularly hard to get both an XX parity and a ZZ parity to work, at least with this current qubit architecture. However, we're currently looking at alternate qubit designs in the superconducting landscape, like fluxonium, heavy fluxonium, Kerr, cat qubits, and so forth. And I think in these other architectures, they have more possibilities for things like this to be implemented. So this may just be a transmon specific issue, that it's hard to do with transmons. It doesn't necessarily kill the idea that it couldn't be done with slightly different architecture.
Okay. Well, thank you so much, Justin. This was extremely clear and very nice in many ways.
Hopefully it was helpful.
By the number of questions we've had, it's been something that's engaged people.
Good.
Yeah, thanks very much.